Let's cut to the chase and talk about GD&T. Why do we need GD&T? So this main significance of GD&T is to control the dimensional variation in parts. So you see, I work on a car called Jeep Wrangler, and every year we make about 80,000 or 90,000 Jeeps, and we sell them out. So what makes each and every Jeep exactly the same? What makes it sure that each and every Jeep has the same quality is because of GD&T. So with GD&T, we control the variation in parts. So there are body panels, there are mounts, and what we do is each and every body panel should look the same, should attach the same. So we do this with the help of GD&T. So when we have less variation, we have less waste. The other significance of GD&T is gap analysis. So consider two parts that go onto a third part, okay, part A and part B. And there is a little bit of gap in between those. Imagine two body panels on the side of the car. On the right side of the car, there are two body panels and they go together on the body. So there is a little bit gap in between them. And how do we perform the gap analysis? That gap can increase or that gap can decrease. So we use GD&T techniques like RSS. It's a statistical method called root sum square for one-dimensional variation. And if it's a three-dimensional variation, we use a software called 3DCS. The third significance of GD&T is to define the locating scheme of the parts. So which is also we call as datum scheme. So what datum scheme does is basically it tells the operator how to attach the part. So A datum or the primary datum would go first, then B datum, and then finally the C datum. So this is how we control the locating scheme of the parts. And finally, there is an organization called ASME, American Society of Mechanical Engineering. So what they do is they every 14-15 years, they will create new norms for GD&T and they will publish it. And we as a GD&T engineers are responsible to go through the norms and make sure we are using the latest current practices in our work. So I mostly work on steering and engine mounts, and I make sure that all my GD&T is in concurrence with the ASME 14.5 2009. The first ASME standard was published in 1994, and the second was published in 2009. And I'm hearing rumor that soon this year or next year, they are going to publish a third ASME standard. It's pretty much the same, just they add some more symbols and just clarify more things. But overall, the basic concepts is the same. So this is an interactive session, and if you have any questions, please make sure you ask any questions in the chat box and Sarang would get back to me. And let's talk about the history of GD&T. So earlier in 1940s or 1930s, there was no GD&T. So is it just the latest fad? No, absolutely not. GD&T is a very technical, very precise way to control the variation of parts. So there is no paper trail as such to see how GD&T was developed, but it is said that an engineer called Stanley Parker in the Royal Torpedo Factory in Alexandria, Scotland. So he is the one who came up concept with the true position in about 1938. True position meaning the position tolerance, what we call right now. And then the position tolerance, then we added the concepts of profile tolerance, flatness, perpendicularity, etc. And that is how GD&T came into picture. And after the World War II, in 1950s, when there was a boom in manufacturing, especially automobile sector, then GD&T was highly used in industry, and that is how it started developing. So why do we need GD&T? What's the use of GD&T? In our general engineering, what we learn is we only learn about size tolerance. So let's say there's a pin over here. And then what we do is we just give 10 plus minus 1 size tolerance. Okay. So if I'm a checker for this part, what I would do is I will touch this point over here. I will touch this point over here. Let's say in the first part, I have 9.97. Part is okay. So basically what it means is that the diameter should lie between 9 to 11. The second part is 10.1 millimeter. As an operator, what I would say, okay, fine. The third part is 10.3, fine. But what I really, as an engineer, what I really wanted to do is I wanted to control the perpendicularity of this pin to this surface. So with this normal callout, with this traditional callout, there is no control over the perpendicularity. On a very bad day, the operator can produce a part something like this. And the checker will touch point 1 over here, point 2 over here, and 9.9. Good, the part is good to go. 10.1, the part is good to go. Is it really what we wanted? No. What I, as an engineer or as a designer, what I wanted is, I wanted this axis to be perpendicular to my surface. That is where the G in GD&T stands for. G means geometric. So it, apart from the size tolerance, also defines the geometry of the part. It defines that, it tells the operator, hey guys, I need this to be perpendicular, not at an angle. So this is why GD&T is necessary. And this is a very simple part. And in industry, there are more complex parts like the steering or the body panels, which require a very tight geometry to be controlled. And that is why GD&T is necessary. So industrial GD&T. Industrial GD&T is slightly different from theoretical GD&T. It's the same, but the main thing is it's highly focused on functional aspects of the part. Meaning that what I have to do is, my only objective in applying GD&T is to make the parts as repeatable as possible. So each and every body panel, each and every door, each and every exhaust system should look the same and should attach in the same way. That is the primary purpose of GD&T in industry. When we have all the parts same, what we do is we standardize the process. With the when we standardize the process, we have a dramatic time savings, because the operator knows exactly how the part is going to attach into my car. A third thing is root cause solving. And this is a very important part in GD&T. So let's say on a very bad day, I'm not able to attach the part. The operator would just raise the flag and ask me to, and call me to the plant and say, hey guys, this is not attaching, and please find the root cause. And then as a GD&T engineer, my job is to find which exact tolerance is causing the problem, or which exact tolerance is not letting me to attach the part in the car. And that is why we have a concept called highest contributor. So we put all the GD&T in the parts, or all the tolerances one below the other, and we put the contributors. So this is 90%, this is 10%, etc., etc. And of course, the 90% contributor will play a major role, will be the culprit in the problem that we are having. And finally, dimensional engineer. So dimensional engineer, believe me, has a very lucrative salary. It's a very nice job. It's a nice behind the desk job. And sometimes you get to go to the plant when there is a problem in the plant. So it's kind of 50%. 50% of the time you have to work behind the desk, and 50% you have to actually go on the line. To me, this is the best job you can ever have in your life. GD&T is used in any manufacturing industry. Believe me, it's used in automobiles, it is used in medical, it is used in electronics. Companies like Apple, Samsung, they use GD&T a lot. And actually in medical industry, the GD&T are very, very tight. It's in the, in automobiles, we have GD&T in form of millimeters. But in medical and electronics, they go as tight as microns. But if you know the basics of GD&T, you can apply it in any manufacturing industry. So having said that, let's talk about the agenda for today. So in this meeting, what we are going to do is we are going to go through 5 different points. So first of all, we are going to talk about feature control frames. Feature control frame, as I like to call it, the language of GD&T. Then we'll talk about datums. Datums is nothing but the building blocks of feature control frame. Then we'll talk about 4 different types of tolerances: flatness, perpendicularity, profile, and position. We'll go through one example to see how these tolerances are added to an actual part. And then at the end, you can ask me any questions you have. Okay. So I'll be taking a quick sip of water. Please bear with me.
So guys, in the meantime, if you have any questions that you would like to ask, doesn't matter how basic it is, please type them in the chat box. And what's going to happen is I would just read out the questions to Prasad and he would answer them for you. All right, yes, so please. Any questions? Like I said, let's try to keep the session interactive, because we really want you to ask meaningful questions to Prasad and also try to answer some of the questions that he may ask. Please carry on, Prasad.
Thank you, Saran. Okay, so let's talk about feature control frame. So if you see any industrial drawing, you must have seen this rectangular boxes pop up near each and every feature or each and every surface. So whenever I say surface, surface is nothing but basically surface is a surface. So if I have a part something like this is a surface. So GD&T controls the surface as well as feature. Feature is nothing but a hole or a pin or a slot or a tab. Anything that you can actually take a vernier caliper and measure end to end, that is a feature. So with GD&T we control two different aspects. We control the surface and we control the feature. Feature meaning hole, pin, slot or a tab. So what does this rectangular thing means? In GD&T, this means a feature control frame. So if I try to write this down, this entire thing into text form, what it will mean that a position tolerance of 0.25 millimeter is to be applied to a circular tolerance zone of feature at max blah 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 blah. The big wordings right over here. Absolutely, there are hundreds of features in every drawing, especially if you see powertrain. The drawings are they have so many holes, so many pins, and I cannot write this text below each and every hole. So what the ASME guys did, that they created something called a symbol to denote this text into a smaller format. And this is the feature control frame. The feature control frame basically consists of 1, 2, 3, 4, 5, 6 different parts. So the first part is the geometric characteristics. The geometric characteristics is nothing but it tells you what type of tolerance I need to apply to the feature. So there are 14 different types of tolerances. How many? 14 different types. Okay. Out of which, they have different symbols for each and every tolerance. For example, flatness has a symbol like this. Perpendicularity has a symbol like this. Position has a symbol like this. And a profile has a symbol like this. And I would say 90% of the drawings has only these 4 symbols, because these 4 symbols kind of take care of all the other tolerances. So these are kind of these are very inclusive and they take care of all the other tolerances as well. So the first segment in feature control frame is basically the tolerance. So here, this is basically the position tolerance. Okay. What it means is that, okay, I need to apply a position tolerance to the hole over here. Then this is the tolerance zone shape. So every tolerance zone, let's say I have an axis over here. It means that, and this is the hole over here. So what this means is that my axis can lie anywhere between a cylindrical tolerance zone of 0.25 millimeter. Okay, so this is what it means. So if it's a circle or if it's a hole or a pin, we use a phi. If it's not a hole or a pin, we just ignore this phi. Okay, phi only denotes that it's a circle, it's a hole or a pin. Then the tolerance size. Tolerance size is basically the actual number of the tolerance that I want. This is always in millimeter. Please note that this is always in millimeter, except specifically mentioned as inches. So let's say I have something like 25 plus minus 1, and then I have a feature control frame of position of, let's say, 1 millimeter back to A, B, and C. Okay, here nothing is mentioned. So by default, I have to assume that 1.0 is in millimeter. But if it's mentioned something like this, then the 1.0 acts in inches. Okay, so 1.0 is a very big tolerance for inches. So if it's in inches, the tolerance is like something like 0.001. But what I'm trying to say is that if it's nothing is mentioned, then you have to consider this number as millimeter. Then comes the material modifier. Today we are not going to talk about material modifier because this is a deep concept. It will require some basic understanding and some basic foundation build-up. So we will not talk about material modifier.
Hey, Prasad.
Hey, Sarang.
Yeah, looks like we have a couple of questions. So the first question is the 0.025 mm, is that a diameter or radius?
It's a diameter.
Okay, thank you. Yeah. And then We have a question from Rahul Kaushik, which is, what exactly is a diamond pin used and what kind of tolerances are taken into consideration to make the pin?
Okay, so diamond pin is, okay, let's say let me just erase this. Oops. So let's say I have a slot over here. And then to give dimension of the slot, what I do is I call out this surface over here or this feature. Okay. And then I give a tolerance of 10 plus minus 1 and whatever the position is. Okay. So tell me, will this have a phi symbol or not? Of course, it won't have because it's not a circle. So it won't have a phi symbol. It will only have a position of 1.0 back to ABC. So, and then I have another tolerance called out in this direction. So what I'm trying to do is I'm trying to control the slot in X direction and I'm trying to control the slot in Y direction. So diamond pin is nothing but a gauge pin. And what it does is that to simulate a datum feature simulator for this slot over here, I will create a diamond pin. So diamond pin will look something like this. Okay. And then regarding the tolerances, so diamond pin is nothing but a gauge pin. So if I have to check this slot over here on a hard gauge, what I would do is I'll create a diamond pin. I will have the size, this size as the virtual condition. Again, this virtual condition, we are not going to discuss about it today, but for today, just assume that we have something called as a virtual condition concept for every tolerance. And that virtual condition would be used to design the pin. So that thickness of the pin, diamond pin, would be the virtual condition of this tolerance. And the width of the pin this way would be the virtual condition of this tolerance. So diamond pin is nothing but a gauge pin used to check the part on a hard gauge. Should I continue? Do you have any questions, Sarah?
So we don't have a follow-up question on that, but we have a new question from Abhishek Arora. So the question is, how are tolerance values decided in general? Right. I know that quality parts have close tolerances, but there may be some general rule that applies to general parts under different working conditions.
Right. That's a very good question. And believe me, when I was on my first day of the job, I had this exact same questions. And the result is, and the answer is actually, there are some specific tolerances based on the supplier that you're working with. So in general, let's say a mount, an engine mount, the A datum will have a flatness of 0.25. Okay, this is a generic tolerance used for any machining part or any machining surface. I can give the tolerance as tight as 0.01 millimeter as well. But then the supplier will raise the cost like $10,000 or something like that for the tooling. So it mostly based on your communication with the supplier, and there is no specific there is no specific standard ASME that says, okay, the flatness should always be 0.25. It's more of about the carryover part. So if the previous parts has 0.25 tolerances, it's going to work in the same way for the new part. And in the next slides, I have example tolerances for machining position, machining flatness, and we'll talk about it. So, but in general, let's say any machining flatness has 0.25 millimeter. A position tolerance generally is 0.5 to 1 millimeter if it's a drill part, and the profile can vary between 1 to 2 millimeter. And this is for an engine mount which doesn't have any, which only has functional aspect. There is no visual aspect to it. But for example, if you consider a knuckle, so a knuckle attaches to a link. Let's say it attaches to the toe link. So that joint is very crucial. So in our company, we give that tolerance, the flatness, as 0.1 millimeter, which is extremely tight and which is extremely costly. So it depends on the function of the part. If it's not so much functional, you can give 0.25, which is perfectly okay. If it's highly functional and you want the part to be perfectly rigid, you can give 0.1 millimeter. Again, this is, as you go into industry, you will learn more and more about the numbers. Am I clear? Yes.
Yep.
Okay. Okay. Do you guys have any more questions, or should I continue?
So for now, please continue, Prasad. I think I'll interrupt you maybe in another 5 to 10 minutes.
Absolutely, no problem. So I hope the feature control frames are okay. Feature control frames, like I said, nothing but a language of GD&T, contains the geometric characteristics, what the tolerance value is, the size or the shape of the tolerance zone, which is always a phi if it's a circle or a hole, and A, B, C are primary, B is the secondary, and C is the tertiary datum. So let's talk about datums. Like I said, datums are the building blocks of any feature control frame. Going back to the feature control frame, ABC are the datums. So datums are used to constrain the part. Whenever I say, okay, operator, Mr. Operator, I have to assemble one part to another part. So what I do is basically I constrain the part. I make sure that the part does not move in any direction. So datums kind of define the locating scheme, gives an idea to the operator how you're going to locate the part, and also it stops the degrees of freedom for any part. Let's talk about degrees of freedom. So take any part, any physical part which has mass and volume. Okay, it has 6 degrees of freedom, meaning that it can translate along XYZ axis and it can rotate along XYZ axis. Okay, so it has 6 degrees of freedom. When we say to assemble the part, when I say I have to assemble the engine mount to the engine, what I do is I constrain this 6 degrees of freedom. So I make sure that the part doesn't move in any of the direction XYZ, or it doesn't rotate in any of the direction XYZ. Okay, so we'll talk about how exactly we constrain the degrees of freedom in a very nice example that I have at the end of this lecture, and that would give you a very good idea as how the degrees of freedom are constrained. So types of datums. The first datum is the primary datum. So primary datum is nothing but, you can say in a very generalized way, you can say that primary datum is the first mating surface. Okay, so let's say I have this block over here and there is a surface over here. And I tell the operator, okay, Mr. Operator, please attach this block to this surface. So obviously this A is the primary datum, so he will attach this surface to this surface first. This is a very generalized way of saying what A datum is. There are more complex ideas to A datum as well, but we will. That is not something we can cover today. We will definitely cover in the lecture series that we are going to have. But for now, just understand that primary datum is nothing but the first surface that mates to another surface of a part. So if it's an engine mount, so engine mount kind of looks like this. So there's a hole, let's say there's a slot and there are 2 oversized holes. And then this is my engine block over here. And then this surface mates to this surface. So this surface would be my primary datum. Primary datum constrains 3 degrees of freedom. So out of 6, it will constrain 3 degrees of freedom always. Secondary datum. Secondary datum is the second surface or the second feature that attaches to my another part. Okay, it can either be a surface or it can either be a feature. Surface meaning just a plane or any surface as the word suggests, and feature meaning any hole, pin, slot or a tab. So primary datum is nothing but the second surface or second feature that would attach to my other mating part. It will constrain 2 degrees of freedom. And finally, there is 1 degree of freedom left. So primary datum A will constrain 3 degrees of freedom. Primary datum B will constrain 2 degrees of freedom. And finally, I have the tertiary datum, secondary datum B would constrain 2 degrees of freedom. And finally, I have a tertiary datum C, which constrain 1 degrees of freedom. 3 plus 2 plus 1, 6 degrees of freedom constraint, and the part is finally assembled to my other meeting part. That is the main goal of any GD&T engineer, is to how to constrain that part completely so that no degrees of freedom is left behind. So this is about datums, and for now, just understand that datums constrains the degrees of freedom. Primary 3, secondary 2, tertiary 1. So let's talk about flatness. So excuse me for a minute, I'll just take a sip of water. Okay, so let's talk about flatness. So flatness is nothing but a tolerance that controls the waviness of a surface. So I have a surface, something like this. In CAD, it will look perfectly a plain line like this, but in reality, it's never a plain line. It always has some kind of waves like this, okay? And as a GD&T engineer, I have to control the flatness. I have to make sure that the part is perfectly plain so that it attaches perfectly to the other mating part. Now, the suppliers are very tricky, and if you don't give any flatness, they will just give any part which has, which the surface finish is something like this. I don't want this. I want this surface to be perfectly plain. But hey, nothing is perfect in this world. Everything has imperfections. So this part also has an imperfection. So what I would say is, that's fine. It's okay, you have imperfections in your surface. I want the imperfections to lie between 2 parallel planes of 0.25 millimeter. So the symbol donated is something like this: flatness 0.25. And I will attach it to this surface over here. So what the supplier would do is he will create a surface, and that surface would lie between these 2 parallel planes of 0.25. 0.25. So let's say as long as the waves of the surface are within this, I'm fine. And suddenly if the waves goes, let's say boop, boop, then the part basically is out of spec and I cannot accept the part. So the flatness is measured with something called a dial gauge indicator. What it does is that it just, the checker just moves the dial gauge from one point all the way to the other point over here. And then he kind of marks 2 points on the dial gauge indicator. And as long as while moving the dial gauge indicator on the surface, the pin of the dial gauge indicator falls in between these 2 marks, then the part is okay. If the pin falls out of those marks, then the part is out of spec and hence I cannot accept it. So for a machining surface, like I said, the flatness 0.25 is perfectly okay. And you can call this out 0.25 on any surface without having an additional cost to the part. But then if you call something like 0.01, then it will dramatically increase the cost to your part. And then your manager will come behind you and ask, why do you have to give such a tight flatness? So for normal parts, 0.25, perfectly okay. And then it is generally given to the primary datum. So, excuse me, let me just clean this up.
So in the meantime, I'll just go over some questions.
Mm-hmm.
So first question is from Samir Gupta. As a design engineer, should a person know the tolerance of every feature, or is it something that the industry will provide us?
Right. So again, the industry will provide us when you go into the company, start working in the company. Within a few days, you will go through, okay, let me give you my example. I was a freshly baked engineer, went directly into the dimensional aspects of industry. I had no idea what the tolerances should be. So the first week, what I did is I just, all I knew is I had to work on mounts and steering systems. So what I did is I went through the previous drawings that were there for the mounts. So basically FCA has been making cars since the last 100 years. So what I did is I went through the drawings in the last 4 or 5 years for the mounts and steering systems, and understood, okay, generally if it's a flatness, we give a 0.25. If it's a position, we give 1 millimeter tolerance. And that is how it's a very based on, highly based on the industrial experience. And of course, your colleagues and your manager would help you out with deciding the numbers. But it cannot be too high. So flatness, to give you an idea, you cannot give a flatness of 1.0, because then the supplier will kind of take advantage of it. And you cannot give this flatness of something like 0.01. Then the cost would be just highly costly. The part would be highly costly. So based on the reference parts, when you go into the industry, this number is decided. Okay.
All right, perfect. So I guess the next question is from Kawaljeet. Is it necessary to have 0 degrees of freedom? Because at the end, the machines have some degrees of freedom.
Right. Again, it depends on part to part. You are right, Kawaljeet. There are some parts which doesn't need to construct all 6 degrees of freedom. Let me give you an example. So let's say I have a rod over here. Okay. And I have a sleeve over here. Oops, I'm sorry. A sleeve over here. And for the functional aspect, I don't know where it can be used, but I want the sleeve to kind of move alongside the rod for the functionality of the entire part. In this case, you don't have to fix all the 6 degrees of freedom. In this case, you won't fix all 6 degrees of freedom. But if it's a rigid part, for example, let's say I'm attaching a bracket to a transmission. In this case, I don't want the bracket to move. So basically, once I torque all these 4 bolts, I don't want the bracket to move in any direction. In this case, you have to constrain all 6 degrees of freedom. Again, it's based on the functional aspects of the part. In this lecture, we are just going with a very simple bracket that needs to be attached to another fixture. So I said that we need to constrain 6 degrees of freedom. But yes, in real life, based on the function, you don't need to constrain all 6 degrees of freedom. Okay.
All right. Thank you so much. So we have 2 more questions. Actually, 3 more. So one is from Rahul J. How is surface tolerance defined in feature controlled frames?
So surface tolerance in the sense profile of a surface, I believe that's what you're asking. So in the next 4th slide, I have called out profile of a surface tolerance, and I'm going to talk about profile of surface tolerance. But to give you an idea how a profile of a surface is called out, it's called out with a symbol, something like this. Okay, so this is for this symbol over here is for the position tolerance. And this symbol over here is for surface profile or profile of a surface. Both mean the same thing. Okay.
All right. So final question for the second Q&A session is from Ajay. What type of symbols are used for weldment and sheet metal parts, especially for bending? I guess he's talking about bending. And for weldment and sheet metal parts, what type of symbols are used?
Okay. So the thing is, again, there are 14 symbols that we have in GD&T. And either of these are used in weldment, either it's in weldment or it's a sheet metal. These 14 symbols are universal. They can be used to any part you want. And based on the functionality of the part, you can pick any of this. So, okay, if you want the, so if let's say you have a plate like this, and then you're going to create a bending operation along this axis. So in the end, you will have a plate which looks something like this. And then you need to control, let's say, the surface over here. You can just give a flatness of whatever the value you want. And that's fine. So these 14 symbols are universal and they can be used for any manufacturing operations you want. Okay.
All right. Okay, Prasad, so you can continue and we'll have just one last Q&A towards the end, okay?
Absolutely. Thank you, Sarah.
All right, guys, so please, pay attention to the presentation. And again, we really like the questions that we're getting. So we'll have one more Q&A session towards the end. So if you have any loaded question, just wait and then ask them. Please go ahead, Prasad.
Thank you, Sarah. So I hope flatness is clear. Again, flatness nothing but controls the waviness of the surface, so that I want a nice and smooth plane surface. Now let's talk about perpendicularity. This is the second form tolerance that is highly used in our GD&T area. So going back to the second slide, if you remember, I talked about a pin and how, as a design engineer, I want the pin to be perfectly perpendicular to the plane. How do I define that? How do I tell the operator or the manufacturer that, hey buddy, I want this pin to be perfectly perpendicular? It is where the perpendicularity kind of comes into play. So what I would do is I would simply put a perpendicularity tolerance on this pin over here. So let's again 10 plus minus 1. I have to give a size tolerance because there is no way that the manufacturer will always make the pin to be 10 millimeter. There has to be size tolerance. Again, this number tolerance is based on your industrial experience, and as you start working in the industry, you will get to know what that tolerance should be. So size tolerance 10 plus minus 1, and I would add a feature control frame over here with a perpendicularity symbol. Okay. I'll just give you 5 seconds to just to realize, should I put a phi symbol over here or not? Should I put a symbol over here or should I not? I hope you guys guess the right thing. Yes, I need to put a phi symbol over here because it's a pin, right? Let's say I want the perpendicularity to be 0.5. And then, okay, I'm saying the pin needs to be perpendicular, but with respect to what? There are hundreds of surfaces in an actual part, but I need this pin to be perpendicular to a specific surface. So I would call that surface as D. So what this means is that it tells the operator that I want this pin. The size can lie anywhere between 9 to 11. And also the axis of the pin should lie between a cylindrical tolerance zone over here of 0.5 millimeter. So this is the cylindrical tolerance zone over here. So basically this is the 0.5, and what I'm saying that the axis can lie either this way, it can lie either this way, or it can be perfectly straight. So that controls the perpendicularity of my feature of my pin back to my surface. So in general, machining perpendicularity 0.5 is perfectly okay. And if I use a feature as my secondary datum, then I generally give a perpendicularity to my secondary datum. But the number 0.5 is perfectly okay, and the supplier should be able to, if it's a drill part, if I'm drilling, the 0.5 is perfectly okay to achieve without any additional cost. Now let's talk about position tolerance. Now position tolerance is kind of tricky. What it does is that it tells me the position for the center of the hole over here back to A, B, and C datum. So I have a part that is fixed completely, and there is a hole over here. And I want to control that position of the center of this hole with respect to A, B, and C datums. So A, B, and C surfaces I have to control. So how would I do that? In this case, the position tolerance comes into place. I specifically picked this picture over here because I wanted to show how the inches are shown. So if you see over here, there is an inch symbol. So obviously the 0.01 is an inch. If we don't have the inch symbol, then it would be a millimeter. So what this feature control frame means is that this symbol stands for the position, that I want the position of the axis of this hole to be in a cylindrical tolerance zone of 0.001 inch in this case with respect to A, B, and C. So what this means is that this axis can lie anywhere between this cylindrical zone. So I'm pretty sure you must have questioned that what's the difference between perpendicularity and position in this case. So the main difference is position does not control the location of my feature over here. So if I had this just as a position, okay, let's not consider the position. If only I have this as a perpendicularity of 0.1 back to A, it does not define the location of this axis. The axis can be anywhere over here. As long as it is perpendicular to A datum, I'm fine. But what position does is that it says, no, I want the position to be within 0.001 inches with respect to A, B, and C datum. So position is nothing but it locates the part. And a machining position is 0.5 is perfectly fine to have without any additional cost. And finally, the most important tolerance is profile of a surface. This is used in body panels a lot because it's a visual aspect. All body panels have visual aspects, and a very tight profile are generally used in the outside or the fascia of the car, or on the outside of the tailgate of the car. So what profile means is that if I have a part that is fixed to my A and B datum, let's say in this case, I only want to constrain 5 degrees of freedom. That's why I don't have a tertiary datum. Okay, I don't have anything called out as C over here. Let's say I have some weird part and I just need to constrain A and B surfaces. It means that this part can come outside the screen. It can go inside the screen perfectly. Okay, because I have not constrained the third surface. So 5 degrees of freedom constraint, but one translation is not constrained. That is, it can slide outside the screen. It can slide inside the screen, but it has a nice wave to it over here like this. And because of visual aspects, I have to control this wave over here. So in general, the what the supplier can do is he can just make a part something like this and give it to me. But I don't want it to be like this. I want the surface to locate in exactly the nominal condition or in the CAD condition. So what I do is I will use a feature control frame, put a profile symbol over here. This is the tolerance zone. Again, should I put a phi over here? Is it a mistake? It's not a mistake. We don't need to put a phi over here because this is not a pin or a hole. Okay, it's just a surface. I don't need to put a phi over here. What it means is that it tells the manufacturer, hey buddy, make sure that you create 2 planes, one this way and another this way, and make sure this surface would lie between these 2 planes whose thickness is 0.03 millimeter. So the surface, let me change the color. So the surface can lie something like this, and it's perfectly fine by me. Okay, as long as it's between the range of 0.03 millimeter. So now I'm pretty sure you must have the question. So what's the difference between flatness and profile? Why do I have 2 different callouts for flatness and the profile? Again, flatness is a local phenomena. It does not control the location of the surface. So let's assume I do not have a profile over here. Oops, let me change the color. Let's say I only have a flatness over here of 0.03 millimeter. So what it would do is that the supplier does not get any idea of the location of this surface. On a very bad day, what he would do is, he will simply create a surface like this. And if I have only called out 0.3 millimeter, he will put 2 surfaces over here like this. And as long as this surface lie between the thickness of this 0.03 millimeter tolerance, he will say, okay, the part is good to go. But do I want the surface over here? No, I want the surface to be located over here, this way. So profile controls the location of the surface. Flatness does not control the location. The location of the surface can be anywhere. It just controls the waviness of the surface. I hope that's clear. This was pretty confusing to me when I started out, but as you start working, get more experience, you kind of understand the subtle differences between these different types of tolerances. So for a machining tolerance, again, you can have anything between 0.5 to 1 is perfectly okay. And the supplier should be able to make any part, a machine part between 0.5 to 1. If you go tighter 0.1, then he will just add cost to it. So up till now, we went through feature control frame, we went through datums, we went through 4 different types of tolerances, just the basic. Flatness controls the waviness, perpendicularity controls the perpendicularity, position controls the position of the feature, and finally the profile controls the shape of the surface and also the location of the surface. And now we are going to use all these concepts that we learned right now in the last 30 minutes in an actual example. So just try to understand what I'm trying to do over here till I take a sip of water. Okay. So this is a very simple part, a plate and a fixture. What I want to do is I want to tell the operator, Mr. Operator, please go ahead, please put this plate onto a fixture with these 2 holes over here. So let's first talk about datums. Any GD&T starts with datums. So the very first thing I would try to do is to define the datums. Okay. This is the primary, secondary, and tertiary, which I call A, B, and C. This, you can use any alphabet in the in our alphabet series. You can use PQR, anything, XYZ, anything you want. But in general, we use A, B, C. So okay, as a design engineer, I want this plate to be fixed onto the fixture, and just by looking at it, I know that this surface over here. Let me change the color. So as a design engineer and in general intuition, I know that this surface over here would first attach to this surface over here. Okay. So tell me which would be my A datum, which is the first surface that attaches to my other mating surface, this bottom surface. Okay. Not this surface, not this side surface, not the top surface, but the bottom surface. That would be my A datum. So imagine you're holding a thick book onto your hand. Okay, you're placing a thick book horizontally on your hand. So you are basically holding the bottom surface of the book. That would be your A datum. Now tell me which 3 degrees of freedom are constrained when you hold the book from the bottom surface. So here's a simple XYZ coordinate system over here. And here's, imagine this is a book and this is the surface of the book. So I'm just holding the book, just placed it on my hand. Can it move along X direction? Can it move along this direction? Yes, it can slide along the X direction easily. Can it slide along Z direction? Okay, can it slide along this direction over here? Can it slide along this direction? It can. I mean, it's sitting on a plane. It can slide along X, it can slide along Z. But can it slide along Y direction? Y direction is basically the up-down direction. Can it go up, down? No, because I am holding it from the bottom surface. So I have stopped the Y translational of that book. Okay, my aim is to make sure that 3 degrees of freedom are constrained. So I know, okay, 1 is definitely constrained. Now let's talk about rotation. Imagine that if you're holding the book from the bottom side, can it rotate along X? Can it rotate like this? If you're holding the book over here, can it rotate along X? No, because it's nicely and firmly sitting on the palm. So I've stopped X rotation? Can it rotate along Z? This surface over here, this axis over here. It cannot rotate because it's firmly sitting on the palm. So it cannot rotate along Z. It cannot rotate along X. But can it rotate along Y? Y being the axis which is perpendicular to the book. Okay, the book is sitting on your hand, Y axis is perpendicular to the book. Can it rotate along the Y axis? It can, because it's just sitting on my hand. So it can rotate along Y. So as you can see, I have constrained 3 degrees of freedom. So I have constrained Y translational, I have constrained X rotational, and I have constrained Z rotational. So 3 degrees of freedom constraint, this would be my A datum. Okay, let me just erase this again so we can talk about B datum next. So I have constrained 3 degrees of freedom with the bottom surface. So I know this bottom surface would be perfect candidate for my A datum. Now I have to constrain the rest of the 3 degrees of freedom. Let's assume that I take this hole as my B datum. Okay, I tell the operator, Mr. Operator, please fix this B datum, B hole over here onto this pin. So imagine you're putting a finger into this B hole over here. Okay, so when you're putting a finger in the B hole, what you do is basically you're constraining the part. So after you are holding the hole, the small hole over here, can it rotate along, can it translate along X? No, because I am fixed this hole over here with my finger. So it cannot translate along X direction. This is the X direction. So I fixed X direction. Can it translate along Z, this direction? It cannot, because I'm holding this hole over here. So this hole over here, so the part cannot move along Z direction. Can it rotate along Y? Y being axis which is perpendicular to the surface of the book over here. Let me change the color. Okay, let's take this one. This is the Y axis. Can it rotate along? Yes, it can, because I've put my finger into the B datum hole and it can rotate along the Y axis. So I still have 1 degrees of freedom left. So 2 degrees of freedom stopped by this hole over here. It's a perfect candidate for my B datum. So A datum, a surface, B datum, a hole. And I know there is 1 degrees of freedom left. How would I constrain that? So obviously the answer is simple. This would be my C datum. So when I put 2 fingers in these two holes over here, the part would be completely constrained. It cannot translate along XYZ. It cannot rotate along XYZ. So this would be my C datum. So that is how we constrain the part. That is how we put datums onto the surface. A datum, the primary surface that will attach to another mating part. B datum, any surface or feature that will stop 2 degrees of freedom. And C datum will constrain the last degrees of freedom. As a GD&T engineer, okay, I have decided the datum scheme. Now I have to put an actual GD&T. I have to create drawings for this part over here, for this plate. So what I would do is I'll open my favorite software, Unigraphics, and I'll create a drawing. So if you see over here, this surface is my primary datum, like we decided in the previous slide, stops 3 degrees of rotation. And I want this surface mates to another part over here. It mates to this part. So I want this surface to be nice and plain. So I will put a flatness of 0.25 to the A datum. So when I put a flatness, this would become my A datum. So even if there are any waviness on this surface, they won't lie outside the 0.25 tolerance zone. Okay, then I have to put a B datum. Once you put a B datum over here, I have to control the perpendicularity of this pin back to A datum. So let's say this isometric view, the manufacturer can make a hole which is something like this. Do I really want this? No, I want it to be perfectly perpendicular. Again, perfect perpendicularity does not exist. I have to give some kind of tolerance to it. So what I say, that's fine. You can have some perpendicularity, but this axis over here should lie between a cylindrical tolerance zone of 0.5 diameter. This is the diameter symbol over here.
Hey Prasad,
Yes,
sorry
sir.
for the interruption. Do you mind just zooming in into the diagram just for this particular slide?
Absolutely, sure. Thanks for letting me know. I didn't understand it, but I hope it's
Sure.
clear now.
Much better.
Okay, so yeah. Okay, so we have fixed the B datum over here, and like I said, I want this hole over here, the smaller hole, to be perpendicular to A datum, and that's why I give a perpendicularity of 0.5 with respect to A. And of course, I have to give some kind of size tolerance, because there's no way the operator can always make 10 millimeter. It will have something like 10 plus minus 0.25. And finally, the C datum or the C hole. Now I want the axis of this hole at a certain position back to A and B datum. So I would use a position tolerance. Again, the position tolerance, it would do is it will ask the axis to lie between a cylindrical tolerance zone of diameter 0.5 millimeter. So the axis can lie anywhere over here, and the center of the hole or the C datum hole would always be in this position between the tolerance zone of 0.5. So I have given a 0.25 flatness to my A datum. A B datum has a perpendicularity. A C datum has a position. A, B, C are fixed. And for visual aspects, let's say this is a car panel, let's say, and I am going to see this surface over here, the surface between P to Q. And I want this surface to have very small imperfections. So what I would do is I would put a profile of tolerance. So what I would do is there should be a C over here. So after what I would say that after you have constrained the part completely with A, B, and C datum, after that, this surface P and Q should lie between two parallel planes of 0.5 thickness. Okay, there shouldn't be a phi symbol over here, because this is not a hole or a slot, and there should be a C datum over here because we have defined all the three datums A, B, and C, and that is how we create the part. So we define A, B, C datum, flatness goes to A datum, perpendicularity goes to B datum, and a position goes to C datum. And the rest of the surface, based on the visual aspects, you can put a tight profile or a loose profile, or what we have something called as a generic profile tolerance. So we say all surfaces profile 0.5. It means it will default, it's by default applicable to all these surfaces. So it's applicable to this surface, this surface, this surface. And if you want a specific surface, you can just put 2 points P to Q and put something like profile of 0.5 back to A, B, C, and between the points P and Q. So this is a simple plate to the fixture example and how to create a JD&T for this plate. Now, as a homework, just something to give you to rack your brains. Here's another example that I have, and let me zoom out. So here's a bolt over here and a nut over here. And let's assume the nut is fixed to a plate, and I want to create GD&T for this bolt over here. Okay, I have to create a GD&T, or of course we'll start with the datums. So how would you define the datum scheme for this bolt over here? Which would be my A datum, which would be my B datum, which will we have any C datum, what tolerances should we give? So this is just an example, a homework example for you guys, and you can kind of go through this and check on the internet how a bolt is put. Believe me, this is different from the fixture, and it's kind of challenging. The point I'm trying to make is that as we go, we'll have more complicated parts, and in the lecture series, what I try to do is I'll try to gather as many examples as possible, We'll cover some examples from body panels, some from engine mounts, some from transmission mounts, steering, exhaust systems, so many parts, so many possibilities, and we'll go through all those examples and try to give you an industrial aspects of GD&T rather than just understanding the theoretical aspects. So here's just a brief introduction of the course that we are planning to do. So we'll start with the introduction of GD&T.
Prasad, just sorry for interrupting. So with respect to the course, I'll be talking about that towards the end. So let's just answer some questions, and then there are some people who are just here to attend the workshop. So we would just tell them about what is the next step. And once I talk about the course from my end, feel free to pitch in any additional points that you want to.
Absolutely. Let's do that.
Okay.
Sure.
All right. So let's take some questions. So the first question, I think, is from Lokesh. And I think this has to do with the surface defects. And it says, what does 0.25 indicate? Is that a range or RMS or average? I think this could have been a much earlier slide. Yeah, I think that's the slide.
This one over here? Or is it a profile?
The profile one, I think. Well, not sure. So Lokesh, if you're hearing us, can you just tell us which slide it is? In the meantime, we'll just jump to the next question from Kavaljit Singh. And I think his question is, what is the difference? Sorry, one datum meant 1 degree is constrained or more because you used two datum planes to show 5 degrees of freedom. I couldn't understand this part.
Okay, I understand. So the thing is, one datum, so the ultimate goal is to constrain 6 degrees of freedom. So in general, like I said, in general, the primary datum will fix 3 degrees, secondary would fix 2 degrees, and tertiary would constrain 1 degree. But these are very generic examples, and there are examples like we discussed about the sleeve and the rod over here, where we don't need to constrain the last degrees of freedom. So again, this is not a rule as such that A should always constrain 3 degrees of freedom. There are examples, and if you kind of give a thought to the bolt and the nut example, you will see that A datum is not what you are expecting. And that is why I want to put a curveball through this example that datums, like I said, 3 to 1 is not always the case. It's a specific case for this plate over here. But the degrees of freedom can vary how you constrain it.
All right. Thank you. So what is, I guess, coming back to Lokesh's question, I think that was the slide on flatness. Okay. That I think you had a number put in like 0.25, and I think, yes, I think this is a slide.
Right. Okay. So when I put 0.25, that is the worst case. This 0.25 is not obtained by any statistical method, or it is not an RMS, or it is not a RSS or root sum square value. It's a worst case value. It means that on a very bad day, the point can lie anywhere between this point to this point. I understand there are ways to get this number using a statistical method that RSS. It's kind of complicated. You have to do so there are Excel sheets called RSS Excel sheets. So it's simple as 1 square plus 2 square plus 3 square, and then take a root of those numbers to get this number over here. But in this specific example, I meant the worst case, that is the extreme case.
All right. Thank you, Prasad. So how will my feature control frame look when I want different tolerances for different datums?
Okay, let's open the feature control frame. So let me start with saying that a feature control frame is specific to one feature. That's why it's called the feature control frame. So it can either be to a surface or to a specific feature. So for datums, for a datum, we generally have a flatness called out back to just a number 0.5. For B datum, we generally have a perpendicularity. For C datum, we generally have a position. And then let's say if this is my plate over here, this one hole over here, and this is two hole over here. This is my B datum, this is my C datum, and there's another hole over here. Here in this case, I have to give a position tolerance back to A, B, and C. So I hope that answers your questions, that every datum has only one specific feature control frame that kind of takes care of the tolerance for that datum.